This is a video over Cramer's rule. So Cramer's rule, first of all, just to discuss, when we have a system of equations, here I have a 2x2 system of linear equations, and I've expressed that as a matrix equation as demonstrated, and I'll call this equation 1. When given such a system, this can extend for higher dimensions, but when given such a system, we often call this the coefficient matrix, and my constants are here, 5 and 3. What I'll be doing with this method is I'll define the determinant of the coefficient matrix, often, so this 2, 4, 3, -2. You'll notice for matrices we usually use a square bracket on the sides, and here I've used those vertical lines. They kind of look like an absolute value for the matrix. We call that the determinant. This notation denotes the determinant, and if you'll remember, the determinant is the product of the main diagonal. 2 times -2 gives you -4 minus the opposite diagonal. So 3 times 4 gives me 12. Here the determinant is -4 minus 12, so I'll have -16. I'm using D for determinant there. That's given here. This can be, you can find the determinant of a matrix using your calculator. It's under the matrix menu. So if you go to the matrix menu, you should have some options, and DET is the determinant. If you type in DET of a matrix, like DET of A, and press enter, it will take the determinant. Under the rules, you need to be using a square matrix and need to know the conditions when the determinant does and does not exist. So given this and passing, making sure that that makes sense, then we'll talk about D1 here. For D1, what I've done is I've taken D and I've replaced the first column with the constants that appeared in my matrix equation, 5, 3. Sometimes we might call this dx because I'm replacing the x values with the constants. And the determinant of that 2x2 would be -10 minus 12. That gives me -22. D2, I'm taking my D, the matrix that I used for in the determinant, the original coefficient matrix, but replacing column 2 with my constants. So like so, and this will give me 6 minus 15, which is -9. So D1 is equal to -22, D2 is equal to -9. Notice that D1 is very similar. We just replaced the first column. D2, I replaced the second column. Sometimes these are called dx and dy, depending on your textbook or your professor, and that's because we're replacing the coefficients for x with the constants or the coefficients for y with the constants. So Cramer's rule states that when you have a 2x2 system set up as the one I just discussed, x is equal to d1 over d and y will be equal to d2 over d. Now if you'll recall from what we did before, d1 was -22 and d was -16. So 22 over 16 is where I get 11 over 8 for x. And for y, d2 was, I take d2 over d. D2 is -9 over -22 gives me, 9 over 16, and that's what gives me 9 over 16. Now, this ordered pair would represent the point of intersection for the two lines that I started with. You could always check your work by substituting these values into that matrix equation 1 that I denoted here. This method, similar to other methods, this will work when, and you'll get a unique solution for x and y when the system is not inconsistent and those two lines are not parallel. In those situations, you would, of course, not get a unique solution.